Just a quick video to explain the hydrogen explosion is the simplest explanation. Occam's razor. Hot graphite has a way of pulling the oxygen atom right out of water only to leave hydrogen gas. We can see the two equations down here. In the first equation, carbon or graphite as a solid reacts with steam, a gas, to make carbon monoxide gas and hydrogen gas. In the second equation, carbon monoxide gas also reacts with steam to make carbon dioxide and another hydrogen gas molecule. Notice the second reaction occurs all in the gas phase, and it is not limited by the surface area of the graphite anymore. Here's a picture of the graphite as it is used in the RBMK fuel or process channels. Think of it as a charcoal briquette with a machined vertical hole in it. Fuel rods are inserted in these holes, but there is water or steam that flows upward in this channel to cool the fuel rods. There is no cladding between the graphite and the steam rising from this hole, and there is 100% contact between the steam and the graphite. Also note that graphite is porous or a lattice material. There is a lot of voids within the graphite block or gas molecules to penetrate inside. For simplicity, we will just assume the graphite surface area is just a vertical cylinder 7 meters long. Here is a table from a paper that discusses the oxidation of graphite and all the 8 reactions involved. For our purposes, we will ignore the reactions with oxygen as we have no oxygen in the RBMK at this time. We only have steam and graphite and no other oxygen-related reaction competition. This first reaction is the charcoal briquette reaction in our backyard grill. The third reaction is the one that produces carbon monoxide and hydrogen gas. The fifth reaction is the one that produces carbon dioxide and hydrogen gas. We can compare the heats of reactions among the reactions and see that reaction 5 requires a lot less heat than 3. So if you have the heat to achieve 3, there is enough heat to achieve 5. Equation 7 shows once hydrogen gas is present, methane may want to form. Equation 8 is splitting water, and it requires twice as much energy as reaction 3. So reaction 3 will run preferentially over reaction 8. Table 2 shows how the reaction rates vary over a temperature range. Most of these reactions are negatively impacted by higher temperatures. As the temperatures increases, the rate decreases except for 3. Reaction 5 doesn't change much over this increasing temperature range. Reaction 7 is also discouraged as temperatures go higher and higher. To extrapolate to 1700 degrees C, or 3 to 4 times hotter than the last value in this table, equation 3 will likely be the dominant reaction. To calculate the graphite surface area in the reactor, calculate the cylindrical area inside the graphite blocks as a rough estimate. Of course, the surface area would be orders of magnitude larger, given the porous nature of graphite and how easily gases would pass through the matrix. The perimeter of a circle is 2 pi r. R is half the diameter, or 0.044 meters. The perimeter times the length of 7 meters gives the surface area for a single fuel channel. And now there are 1,661 fuel channels, so multiply that out for about 3,200 square meters of surface area, excluding control rod channels. From our handy dandy strip chart, after the MCP fails in the red trend, flow M in yellow, the steam flow climbs from 0 to 600 kgs per second in 1 second. Note the typo on the strip chart. It's 123.45, not 124.45. And 1 second increment is 1 grid line on the chart time scale. Taking a rough estimate, say 600 kgs per second in 3 seconds provides 1,800 kgs of steam flowing through the fuel channels. Steam pressure in trend C, also in yellow, is going through the roof, and temperature in magenta trend N in the fuel channel is already 1700 degrees C by the time the MCP fails. So going back to our calculation sheet, 3,200 square feet of surface area of graphite in contact with 1,800 kgs of steam with a factor of 0.005 conversion rate gives about 28,908 kgs of hydrogen gas. The Hindenburg only had 18,000 kgs. Although there are many variables that can be tweaked to get a more exact figure, this example illustrates how quickly hydrogen gas can be generated in the conditions created after the MCP pump failed. This seems like the most simple explanation for the production of hydrogen gas, so I'm not sure why this might still be controversial means for an explosion. Feel free to leave comments below. As to whether Dyatlov knew this was a hydrogen explosion in the fuel process channels, it is more likely that he did rather than he didn't. He likely knew the fuel channels had gone dry, 100% steam, and the fuel temperature was high enough to make significant hydrogen gas. In the early 80s, cover-ups had become a routine matter at the Chernobyl plant, and no doubt Dyatlov knew the drill. But he didn't want to cause a panic. Cutting off the phone lines had come to be routine, and heading to the bunker was the only means to notify the plant manager. By the way, this image of the plant manager in the bunker at 2:15 a.m. always bothered me. Based on this, he could have gotten a phone call around 2 a.m. or earlier. Since Dyatlov likely made the call, that puts Dyatlov in the bunker about 20 minutes after the explosion. So if you have any insights on this photo or any comments on how soon Dyatlov may have reached the bunker, please leave it in the comments below.